Welcome back to the CritMedic podcast. I'm your host, Dominic Wallenczak, and we're going to talk about cardiology and an introduction to the cardiac anatomy and electrophysiology. So a couple of friends asked me if I could talk about cardiology and EKGs. So I figured what better time to launch a new cardiac series than February, which is supposed to be Heart Month. So we're going to cover cardiology. Bear with me here, I just reformatted my system, so I'm still trying to piece everything back together. So cardiology, stay tuned. So when we're talking about cardiac things, we're talking about EKGs in the context of EMS. And a lot of paramedics may not have had 12-lead education in their initial program. Some programs don't really dwell on 12 leads, don't really dwell on cardiology, which is really unfortunate because it's really a mainstay of what we do. So we're going to pick up the pieces. We're going to start from the very beginning. We're going to talk about cardiology, anatomy and physiology, and electrophysiology. And a lot of you may say, well, isn't that a little bit too easy? Isn't that a little bit too elementary? Well, I mean, it may be, but we have to start somewhere. And don't worry, it's going to get more in depth. So we'll start off light, and we'll get a little bit heavier. So to start off, let's talk about building the perfect human. Now, we're going to take a Build-A-Bear idea and just apply it to humans. Let's pretend for a moment that we are that we are God, or that we are Mother Nature, or whatever deity you choose to believe is in charge of the development of humans. So we're going to develop the perfect human. So looking back at insects really oxygenate their tissue through these small little ducts and channels. So back during the Precambrian period, when the oxygen concentration was actually fairly high, you had actually fairly large insects because the oxygen could diffuse through all the tissues. From the outside to the inside. But since we only have 20% oxygen now at this point, we can't have insects that were quite as large as during prehistoric times. So we're going to have to do something better. We're going to have to come up with a series of tubes. And not the internet. We're going to have to talk about a series of pipes that can carry some sort of oxygen-carrying medium to all the tissues that need it. And it's going to need a lot of tubes. In fact, the amount of blood vessels inside the human body is enough to stretch around the world 3 times, if you lay them all end to end. It is an astronomical amount of tubing to work with. So how are we going to plumb all these pipes? What are we going to do? How are we going to get all this fluid around? That seems like a fairly large challenge. So what we're going to do is we're going to whiteboard this. Let's come up with an idea. Let's brainstorm here. So let's take a pump, and let's send it to let's just plug it in and run it to all the pipes. Oh, wait a minute, we didn't put a radiator in the process, to diffuse the oxygen back into the blood medium. Okay, wait a minute, I've got an idea. Let's start again. Let's take our pump, let's pump it to our radiator, and let's then pump it down to the rest of the body. But wait a minute, there will be a bit of a pressure drop going through the radiator because of all the small tubes. So it will just kind of trickle into the body. Well, that won't work. All right, let's try this idea. Let's take the pump, let's pump it up to the radiator, and then let's have it go back down to another pump that puts it to the rest of the body. That'll work. The only downside is, the pressure loss going into those pumps. You're not going to get the fluid going in quite as fast. So we need to put in a little reservoir and a little booster pump in there so that the fluid can accumulate and get shoved right into that pump, because we need that pump to be full as possible. I mean, just look at that accordion. If it's not all the way up and reinflated, you're not going to get effective squeeze. So we really need that atrial kick. And why do we need this atrial kick, as we call it? Well, it's something called the Frank-Starling mechanism. Essentially, to summarize, what it means is when you have heart tissue that's stretched and under a little bit of tension, it's actually going to contract a little bit more forcefully and eject a little bit more volume. So it's a little bit more effective if you have a little bit more blood inside the ventricle. And that's why it's important that we have the atrial kick. Let's see if we can have a video demonstration of atrial kick in action. So right now the blood's just passively diffusing into all the tissues. Passively flowing into the ventricles. All right, now the atria are doing their power packing. Can you imagine being this guy, though? Your job description is literally to shove people off subway platforms and into trains. At least they got white gloves. Anyways, we get the idea. And the idea is that these atria really cram in all the blood into the ventricles, try and get every last little bit of ounce of productivity out of those ventricles. So when we take a look at the diagram of a heart, it looks fairly complicated. It's got all these labels, and it seems a little bit daunting at first, but we can break it down with that analogy that we used earlier. You can look at it really as a simple set of components. You've got your body pump and your lung pump, you've got your body pipe and your oxygen radiator, and you've got your booster pumps. But even this is a little bit too convoluted and has a lot of twisting tubies and things at the top there. So let's simplify it even further. Let's say this is what we're going to use to represent the heart. It's almost an accurate representation. I mean, I'm no artist, so you're going to have to bear with me on this one. So let's see if we can simplify this. We've got our right atrium, right ventricle, and left ventricle. Pretty straightforward. And just so you know, the reason that the right side's on the left is because it's from the patient's perspective. The patient's right versus the patient's left. So how do we wire this all up? How are we going to provide energy to this pump and, coordinate it with all these different, some pumps and all these different booster pumps? How are we going to coordinate it with wires and electricity? And just as an FYI, this is the Apollo guidance computer from the original Apollo missions. So how do we wire it up? Well, let's put in a little microprocessor, a little chip right at the top, and we'll just have it, fire from there and just depolarize the entire heart. It can do that, cell by cell, domino by domino. But if we're talking about cell by cell depolarization, it's going to start at the top and it's going to work its way down to the bottom. Well, all the vessels that we need are right at the top. So if we do it that way, it's going to look a little bit like this, which is not going to be super effective for pumping out a lot of fluid. So we're going to have to rechannel that energy somewhere. So let's take that chip and let's put some wires in there, just to go through all the booster pumps. And then let's put in a little resistor because we want the atria to do their atrial kick thing before the train leaves, right? So we want to give it a moment to have a little resistor. And then we need to squeeze from the bottom of the heart. In fact, we need to squeeze the entire heart. So we need to put some channels in there so that we can depolarize or squeeze the entire ventricles all at once. Let's put some finer ones in there just so that we make sure we get the energy all down into all the tissues there. So that's essentially, what we did. We start off with the sinoatrial node, or SA node for short, and then we have a number of these pathways. We've got the posterior, we've got the middle internodal pathways, we've got the Bachmann's bundle, and there's this little anterior intraatrial pathway. But nobody has to remember that. In fact, all you really need to know is that there's a bunch of these internodal pathways, is what you can call them. And that leads down to the AV junction, or AV node. And right below it, we have the bundle of hers, the bundle of his. So the bundle of his is right below that. And the function of this is essentially provides a little bit of resistance and a little bit of delay so that, like I mentioned, the atria can fire first and be more effective as far as preloading the ventricles. So we have the left posterior fascicle, we've got the left anterior fascicle. These come off of, together, what is known as the left bundle branch. Meanwhile, on the right side, we only have one fascicle, so it's the one right bundle branch. The left ventricles have a lot of muscle tissue, so it's got a lot more muscle that it needs to depolarize at once. So it has to have that extra pathway just to make sure everything is symmetrical as far as the contraction. The right ventricle, it only has to pump to the lungs, so it's really not as muscular. It doesn't have as much to depolarize. And of course, we've got our Purkinje fibers, which are sort of like the arterial roads after you come off the highway. You come off the big interstate and now you're on your big city roads. And you eventually get down into your smaller subdivisions and your streets and into your little residential subdivisions and courts. And that's essentially what the cardiac electrical pathways resemble. But wait, if the heart muscles can depolarize each other, then why doesn't the atria just depolarize the ventricle? Well, that's a good question. And the reason is that there's this. It's called the fibrous skeleton. Essentially, it's a bit of tissue where all the valves are located. And it's a keratinous structure that really doesn't have a lot of electrical conduction capabilities. In fact, it's essentially a resistor. So really what it looks like is we took the top of the heart and the bottom of the heart, separated them electrically, and we have this little resistor. Now, of course, the fibrous skeleton has lots of other functions too, to add some structure and stability to the heart. But one of the other features of the fibrous skeleton is that it prevents some electrical conduction from the atria down to the ventricles, except for the places where we ordinarily want this to occur. So we've covered some of the anatomy here. Let's go deeper. All right, this is just some of the surface anatomy. Let's go down deeper to, say, the cellular level. By the way, this is not heart cells. I couldn't find a good picture of heart cells. This is actually an onion. So, but besides that point, we're going to go down to the cellular level. So there's some cell properties that I used to teach as part of the 12-week EKG technician course at a community college. So I came up with I used a little mnemonic. I learned this from my original EMT basic instructor at the same college, and I thought it was a phenomenal tool for remembering this. So I taught the 12-week EKG technician course at Erie Community College, which is abbreviated as ECC. Now, Erie Community College, is that Harvard? Is it the best school ever? No, it's definitely not. Is it a diploma mill? No, it's not that either. So what kind of school is ECC? It's an all right school. So that's the abbreviation that I use. Specifically, based on that, it's ECC is all right. Yes, I know all right is one word, but just bear with it for now. So the cell properties are elasticity, contractility, conductivity, automaticity, and rhythmicity. And we're going to go through these one by one just so you fully understand what these properties are. So let's start off with elasticity. Now, does anyone remember Stretch Armstrong? Am I dating myself? Well, Stretch Armstrong used to be a toy, and the big selling point was that it would stretch and stretch and it would return back to its normal shape. And that's essentially what the cardiac properties are of the cardiac myocytes. They stretch. In fact, they work best under a little bit of stretch, and then they return back to their normal shape. That's the property of elasticity. Contractility, well, it shares that with any other skeletal muscle. A heart muscle can obviously contract. Now, conductivity, heart muscle is uniquely able to conduct electrical impulses very efficiently from cell to cell and even amongst the entire structure. So conductivity, the heart cells actually have quite the unique capacity for. Now, automaticity refers to its ability to generate spontaneously a depolarization impulse on its own. You don't necessarily need your nerve cells and your brain to tell your heart to beat. It's going to do its own thing. And in fact, if some cells of the heart that are supposed to be controlling it aren't beating, well, then something else is going to pick up somewhere else, and it's going to tell it to beat there. And the last is rhythmicity. The heartbeat is ordinarily a regular, constant occurrence and has a regular frequency and beat to it. In fact, you could call it regularity if you wanted to. So those are the components of the heart myocytes. But we're going to have to go deeper still. We're going to have to go down to the subcellular level. So here we go. So this is a myocardial membrane action potential. Now, why do I feel that this is important to even mention? Why do I even bring this up? Because this chart's going to be useful for when we explain how different drugs, how different calcium channel blockers, how different sodium channel blockers, how they work and what impact they have on the cell and why they do what they do. So let's cover the myocardial membrane action potential. This is specific to a cardiac muscle myocyte. So typically, the resting level is at negative 90 millivolts. And yes, I know I didn't label my axis here. My math teacher would have a fit. But so the left side axis is your millivolts, and your right side there is time. The typical time frame for an entire action cycle is about 300 milliseconds, give or take. So what happens here, we're going to start off with phase 0. A lot of people start off with phase 4, but it doesn't seem very congruent when you're starting with 4 as far as the numbering system. We're going to start with phase 0. And mathematically speaking, 0 is the first number. Think of, D-Day, 0 hour. 0 is what we start with. So this is when things actually happen. This is when stuff is going down. And what happens is you start off with a little bit of depolarization that causes the full cascade. And you have sodium coming to the cell. Let's illustrate this on our little cardiac myocyte. And again, I am not an artist, so I use some clip art to help illustrate the point. This is the heart. And the inside of the heart is represented with bananas because it's high in potassium. The outside, it has sodium and some calcium. So what happens with the beginning of phase 0 is some sodium, or sometimes a little bit of calcium, enters the cell in the very early portion of the depolarization. If you look on the left-hand side, the very first portion of the line represented in orange, which is not really a good contrasting color here, but bear with me. The first depolarization, once the electrical level gets to about negative 70, you get the full-on cascade of rapid sodium influx. So now all the sodium rushes into the cell. And it comes from, the original sodium comes from a neighboring cell, either through a pacemaker cell or an electrical cell or through another muscle cell. They're connected all together via what's called gap junctions. So when one cell depolarizes, all the sodium rushes into one of these cells. Some of the sodium also goes into the neighboring cell and causes the depolarization next door. So this is how the heart can depolarize cell by cell. So all the sodium has rushed in via these sodium voltage regulated or voltage gated channels. So now we've got a very positive level. It hits up to it goes from negative 90 to positive 30. And from there, we go to the next stage. So we go to phase 1. Phase 1 is an early repolarization. This happens when the sodium channels close, and as soon as the energy level goes positive, our potassium channels open. So you get a little bit of a dip. So what happens, as you can see here on the right, we've got some of our potassium leaving. So that's why we get a little bit of a dip. It comes back down to just a little bit of a positive level. And, that summarizes the phase 1. Phase 2 is what we call the plateau phase. Now, some people represent it as a straight line. It actually has a little bit of a diminishing electrical potential, so it's not completely flat. It's got a little bit of a slope to it. So phase 2, now calcium enters the cell. So calcium enters and potassium exits. So there goes the potassium, and here comes the calcium. Now, calcium is what causes the actual muscle contraction. But the calcium that comes in isn't enough to really cause that contraction. So where does this come from? Well, what happens is the calcium that comes in causes something called the sarcoplasmic reticulum, which I think I've covered sometime before, but the sarcoplasmic reticulum is actually a big bag of calcium. And when the calcium comes in from outside, it causes a release of the intracellular calcium all throughout the cell, about halfway through the plateau phase, and causes cellular depolarization, cellular contraction. So that's what causes the muscles to squeeze. So now that we've done that, now we need to reset and get ready for the next impulse, because that's part of the heart muscle function. It has to keep going. So what happens next is now we have phase 3, the repolarization, which is a mass potassium exit. Well, I want to say mass, but it's the significant amount of potassium that leaves the cell. And this potassium leaving the cell causes the overall level to be more negative. Now, as the level drops, the calcium channels close, the sarcoplasmic reticulum starts its job of mopping up the spilled milk on the inside, and we have several active transport mechanisms going on. Specifically, towards the end of phase 3, beginning of what we call phase 4, which is the resting membrane potential, we have these come on. And yes, they are fidget spinners, but just bear with me for the clip art. I don't have anything that really accurately represents this. So let's talk about these fidget spinners. This first one here is the sodium-potassium ATPase pump. And what that means is it uses ATP, or the energy of the heart cell, which is generally derived not from glucose and sugar, but it's more derived from fatty acids and amino acids. As little as, I believe it's 9% of the myocardial ATP is generated from glucose, so it's not a really significant portion. So this uses energy to move sodium from inside the cell and the potassium from outside the cell against their concentration gradient and back into the cell or out of the cell, respectively. It typically moves out 3 units of sodium and brings in 2 of potassium. And this one over here is the sodium-calcium exchanger. And this actually doesn't use ATP. It just uses the native energy between sodium and calcium and actually causes the exchange of those from intracellular and extracellular. So let's see how this works. So you've got our sodium and calcium switching places. But wait, didn't we just add more sodium? Isn't that what causes the cell to be positive? Well, at the same time, while this is going on and the calcium is being kicked out, sure, a little bit of sodium comes in, but a lot of sodium is being kicked out at the same time through this pump, and potassium is being brought back in. And all in all, this is a net neutral exchange, so you don't really see a significant shift of the electrical baseline. So phase 4, early part of phase 4, end of phase 3 is when you get the shift of all the electrolytes back to their native states and being ready for the next depolarization. So this is what the myocardial membrane potential looks like for a regular cardiac muscle cell. The cardiac pacemaker cell action potential is a little bit different. Now, these pacemaker cells are a little bit leaky. They don't stay at negative 90 millivolts. Their energy continues to climb, and in case of, say, like an SA node, the energy climbs to about negative 40, and at that point, it spontaneously depolarizes. So it has only a phase 4, 0, 3, and 4. It doesn't have a phase 1 or phase 2. So it has this rhythm, almost like a sine wave pattern to it, where it just continues to leak and spontaneously get to the point of depolarization. So it looks a little bit different from what you're typically accustomed to seeing when you look at a cardiac myocyte. So let's put it all together. Oh God, that green is a little bit too bright. I apologize for that. So this is a chart from Braunwald's cardiology, and there is some correlation to the EKG. You start off with the sinus node firing, and it goes through the atria, then it goes through the AV nodes. And you can see how all these waveforms sort of correlate. But keep in mind there are some limitations to this. This, just because these seem to line up at the same time frame, doesn't mean that they're necessarily all directly responsible for it. Obviously, the big spike is consistent with the mass depolarization, but the direction and size is really more dependent on the direction of all these cells depolarizing than it is just based on the overall action potential. The size, amplitude, shape, it's all to do with energy vectors and the way that the energy is going. So this doesn't quite exactly explain it, but you can see overall where things would line up. So hopefully that covers a little bit of cardiology for you, the introduction. We're going to go a little bit more in depth next time, and we're going to cover the EKG development in history, how we got the EKG. We're going to introduce you to the EKG waveform, talk about the EKG technology, and we're going to talk about each component of the EKG, what its normal values are, what it looks like. Then we're going to conceptualize the EKG vectors, essentially making it more easily understandable why the energy moves in a certain direction and what it represents on the EKG. We're going to show you a normal EKG, and then we're going to talk about your different sinus, atrial, junctional, ventricular rhythms, and so on. So I'm not sure if that's all going to be in the next section, but it's all going to be coming up shortly. So hopefully, you've gained something from this, and you'll join us next time for the rest of the Cardiac Academy series. Until next time, take care.